Tēnā koutou katoa, ko Philbrema toka inua, no mai, haere mai. As Acting Deputy Vice-Chancellor Academic, it is my great pleasure to welcome you here tonight to celebrate Professor Cullen's achievements. I'd especially like to welcome Professor Cullen's family, his wife Elizabeth, daughter Susanna, mother Anna, sister Emma Davis, and brother Marcus Cullen. I'm delighted that you are able to join us today on this very special occasion. I'd also like to acknowledge Professor Cullen's father, Roger Cullen, who passed away exactly 1 year ago today. Nicolas, I'm confident that he was very proud of your achievements. It's not easy to become a professor at the University of Otago. The title professor is reserved for the highest achieving academics. It takes ability, commitment, and hard work to become a professor. You need to be able to demonstrate that you're a leader in your field of research, an outstanding teacher, and that you're providing significant service to the academic and wider community. As you will hear tonight, Dr. Cullen clearly earned the title of Professor. Professor Cullen's research has provided us with a better understanding of the impact of anthropogenic and climatic variability on precipitation and snowmelt in alpine regions and their associated global repercussions. The wide range of service roles Professor Cullen carries out for the benefit of his school, the Division of Humanities, the university, and the wider academic and general community is impressive. Professor Cullen has also received some excellent teaching evaluations from a range of popular undergraduate papers he teaches, and he has a strong record of mentoring and supporting postgraduate students. I now invite Professor Rachel Sprocken-Smith from the Higher Education Development Centre to formally introduce Professor Cullen.
Tēnā koutou, tēnā koutou, tēnā koutou katoa, ngā mihi nui ki a koutou katoa. Ko Rachel Sprocken-Smith tākou ingoa. And it's my pleasure and privilege to introduce Professor Nicolas Cullen. Normally it would be done by a senior academic in his department, but with a few departures they've called on me, and I have a very special place in Nicolas's career. So Nicolas was my very first master's student when I lectured in the geography department at the University of Canterbury. And indeed, this was his thesis. Surface-atmosphere interactions over regenerating vegetation in the Hoonhay Valley of the Port Hills. Despite having me as a very green supervisor, Nicolas completed his Master of Science with honours and then went on to the University of Colorado, where he began his work in icy environments, with his PhD on characteristics of the atmospheric boundary layer at Summit, Greenland. After completing his PhD, he went on to do 2 postdoctoral fellowships, the first at Colorado and the second at the University of Innsbruck, Austria. The second postdoc was perhaps more successful, given that towards the end he met Lisa, his wife. So she has been with him for the journey here to Otago, as in 2006 he accepted a position as lecturer in the School of Geography. Nicolas has enjoyed an academic career characterised by research mobility, mountains and other icy environments. He has conducted field work in Antarctica, Greenland, Tanzania, with 6 field expeditions on Kilimanjaro, and of course here in the Southern Alps. His research spans the subfields of meteorology and climatology, with a current focus on understanding how the coldest regions of the Earth are responding to climate change. His focus is motivated by the urgent need to assess the impacts of ice loss from glaciers and ice sheets on sea level rise and the decline of seasonal snow on water resources. Nicolas has been involved in numerous national and international projects, has nearly 80 peer-reviewed publications, and has supervised nearly 40 graduate students. His supervisory capabilities were recognised with the New Zealand Geographical Society's President's Award for Outstanding Graduate Supervision in 2015. He's also a passionate teacher, working to instil climate literacy in undergraduates and generating a framework of courses that introduce students to key aspects of climate change. He is instrumental in promoting international exchange opportunities for his students and helped establish a new student exchange agreement between Otago and Erlangen University in Germany. One of his distinctions is gaining an Erasmus Award this year at Erlangen to focus on research-informed teaching and climatology. He has also held a Mercator Fellowship awarded by a German research foundation to enable intensive, long-term project-based collaboration with researchers at Erlangen, and from 2016 to 2018 held an Alexander von Humboldt Research Fellowship for long-term research in Germany. Alongside his outstanding research supervision and teaching, he's actively involved in a range of service roles, from co-leading the School of Geography through to membership of key university boards and committees, as well as membership and significant roles in professional associations. Hopefully you're starting to form a picture of Nicolas, not just as a researcher climbing mountains and chasing ice, but also as an extremely dedicated teacher and supervisor, and one who is actively contributing to his university and professional communities. Without further ado, I will hand over to Nicolas, who is going to talk about chasing ice in a warming world. He will reflect on the scientific journey he has taken with colleagues, students, family and friends to chase the remaining ice still found in our frozen landscapes in an effort to better understand the future fate of the cryosphere in our warming world. Nicolas.
Tēnā koutou, tēnā koutou, tēnā koutou katoa. Thank you, Phil and Jessica, for coming this evening to support me, and Rachel for your very kind words. To my esteemed colleagues, students and friends, thank you for taking some time to come and listen to me this evening. I would especially like to welcome my family, who have already been introduced, who have travelled from Christchurch. I should also mention Chris and Marie, who've come to do that. It's lovely to see you here. And to my Swedish family who might be zooming in and listening to me from afar. And I also just want to say a heartfelt thank you to my wife Lisa and Susie, my daughter, for your love and support and on this little journey that we've really shared together. So tonight I'm going to talk a little bit about my journey chasing ice in this warming world. And I thought I'd just begin with this figure here, which is fairly familiar to most people these days, which is the global temperature record. And you can see from 1880 through to the present, and this is a temperature anomaly, that our world has warmed. The most recent winter is the warmest winter on record, and 2023 is certainly tracking to be the warmest year on record. And when I reflect on this little figure, I look at that period in particular because there's a lot of red, and it also is the time that I've been on this earth. Since 1971, things have kind of gone into the red, and that's the journey that I want to talk to you about today, and how our perception of that has changed even in my little lifetime. So I'm a climatologist, as Rachel mentioned, and my interest is certainly first and foremost in the atmosphere and how it interacts with other parts of the climate system, the oceans, the biosphere, land surfaces, but most importantly for me, I guess, is the cryosphere, those regions on Earth that are covered in snow or ice. And their importance, they're really fairly critical to our climate system, mostly because they reflect a lot of the sun's energy. When we have a white surface or a snow-covered surface, much of that sunlight that comes is reflected immediately back into space. And so if you have ice, if you have snow on a surface, it controls that climate system to some degree. And we're seeing changes, of course, to that because of this warming. So the talk today, I decided to break up into three little parts or chapters. The first, I want to begin in the 1970s. 1971 was the year that I was born, and talk a little bit about a myth, the global cooling myth, which some of you might remember, and then the advancing glaciers in our own backyard. And then the second part will be the Greenland ice sheet. It awakens, and that coincided with the time that I started my PhD, and talk a little bit about tropical glaciers and the journey that I had on Kilimanjaro. And then that final chapter, which is mostly about mountain glaciers in the Southern Alps, which has been my focus since I've been at Otago. But all of those places have actually been part of my world while I've been at Otago, but they're sort of separated in chapters here just for convenience. So let's start back in the 1970s. I was born in 1971, and there was plenty of evidence even at that time that our Earth might end up warming up a reasonable amount because of greenhouse gases. It was nothing new. In fact, a Swedish physical chemist, Svante Arrhenius, first proposed that if we put greenhouse gases into our atmosphere, it could impact our climate and lead to a global warming. And this was back in the late 1800s. So in the 70s, there was plenty of knowledge, but it wasn't that accessible to the public, and it wasn't something that we were thinking about. But I did a quick search, and there was plenty of literature out there focusing on this carbon dioxide problem and the greenhouse effect. And so if we think of that global temperature record again, of course we focus on that, and it's understandable. It's been a massive rise in temperature since that period of time. But that myth about global cooling had a little bit to do with that part. From the 1940s or the mid-1940s through to the early 1970s, there wasn't that much warming. In fact, it flattened out a little bit, even though greenhouse gases were increasing. And the reason they think that occurred was because after World War II, with all the industrial activity that was occurring, there were a lot of aerosols, sulfate aerosols primarily, being put into the atmosphere, which were reflecting sunlight. They also think there's a little bit of a natural variability inside that signal, but it leveled off a little. And so the popular media got onto that, and I remember this as a child growing up in the 1970s, that we might be heading for another ice age. There was cooling going on. But it wasn't really supported by the literature. Others have gone back, and you can see from this figure here the number of publications at the time from 1965 to the late 1970s. And the red line here is published papers associated with this idea that the Earth will warm because of greenhouse gases. And then the other around the cooling, the imminent next ice age, which was being discussed by some. And then there was another thing that was going on at that time, and it was the fear of nuclear war. We grew up, I think, in the 70s and early 80s actually worrying about nuclear war. And one of the implications of that, if it occurred, would be that we might be plunged into a global cooling or some kind of climatic cooling as associated with nuclear war. Very different to how we think about things today, I think. The other interesting thing that was going on in New Zealand too at that time, at the beginning of the 1980s, some of our glaciers, at least 50 or so, started advancing. And we've got quite careful records of that. And that continued to about the mid-2000s. So not only was there the perception that the Earth might be cooling, little old New Zealand had glaciers that were also advancing at that time. And we think that's probably mostly associated with a slight cooling in the New Zealand region, and that the sea surface temperatures were a little bit lower than normal. So that set the scene for me growing up back in the 1980s at school. Here's a photo of me. This is the first I could find from Standard 3 and through to intermediate. And then I ended up at Boys High, Christchurch Boys High School. And this is my third form picture. And this is how I looked at the end of all of that 5 years later. And I liked school, and I quite liked studying, and it was a different time, I think. And I can reiterate, we certainly weren't worrying about global warming at that point. If anything, as I said, perhaps that imminent new ice age was on its way. The one thing about school was that I always had a little bit of a passion for skiing, and you'll see the back on the wall there's a poster. A poster of a skier. And so while I enjoyed my study, our family certainly enjoyed escaping from Christchurch and heading up into the hills to a place called Craigieburn Valley, which is about an hour and a half west of Christchurch, to a place called Craigieburn Valley. And this is probably where my passion for snow and ice began. My father introduced us all to this. He discovered the place in his late 50s and spent a lot of time up there. Him and his friend ended up acquiring a hut, Whare Awatea, and it burnt down, but they rebuilt it the year I was born in 1970-71. And that became a bit of a centre for our family. And I also enjoyed that period, and I'm probably best remembered for my exploits in speed skiing rather than my academic achievements. And this is a gang of us in the late 80s with our speed skis. And it was at the end of school that I decided, rather than go directly to university, I'd head to Sweden, following my dream to become a bit of a skier. But also, it was an important period in my life because I went and lived with my Swedish family and learnt my mother's tongue, Swedish, and spent a considerable time with my Swedish family. But after that, I ended up back in Christchurch doing my undergraduate degree and then my master's degree with Rachel in the Hoon Hay Valley. And I was lucky because Rachel had just come from UBC in Canada and had worked with we should say famous boundary layer meteorologist, Tim Oak, who had really set the scene and the benchmark for boundary layer meteorology. So Rachel rolled in and I felt really lucky to be able to work with her on a problem which was really focusing on the microclimate of this little valley. And I think we're on a good thing there, Rachel, actually all those years ago. Indigenous vegetation, trying to understand what the microclimate would be, thinking about how regeneration of indigenous vegetation is important. And I think we're still grappling with those things today. One of the big outcomes for that was to set up a series of weather stations, and this is kind of the beginning of what became a bit of a backbone to what I really do. And I would say it was fairly ambitious. We set up 2 permanent towers in that valley, a Bowen ratio system which measures the energy and water fluxes, and that allowed us to look at evaporation and heat transfers over that indigenous vegetation, as well as a mobile tower. And it was that training that really set me up for some of the next chapters in my life. During that time, though, one of my fondest memories of that period doing my undergraduate and master's degrees were the escape to the mountains. And like many of my graduate students today, I would be looking at weather maps in between lectures, and as soon as a high pressure came along, I would try and escape. And I spent a lot of time in the Southern Alps, especially in the Canterbury region, doing lots of recreational climbing at that time, which was building my passion for understanding how these unique systems were behaving. So that takes me to sort of the second chapter, the Greenland ice sheet awakens and the demise of tropical glaciers. And I arrived there and started my PhD in 1999. And it was a fantastic period and a really interesting period because things were changing really rapidly. So when I arrived, the consensus at that time was that the ice sheets were basically in balance. And I had to check this actually. I remembered it, but I went back to the IPCC reports just to confirm it. And it's true. Like the thought at that time was that they were in equilibrium. They weren't growing or shrinking. And even though they were aware that the greenhouse gases were likely to impact the climate, which would then lead to a response from the ice sheets, they were certainly still thinking they were in equilibrium. It was the same again in the 1995 IPCC report. IPCC, I should say, is the Intergovernmental Panel for Climate Change. The United Nations, since 1990, have been producing these sort of state of the climate reports every 5 years or so. And sort of they're our benchmark in terms of our understanding of what is happening to our climate system. And they were still thinking perhaps because the world might be warmer that it would increase precipitation, so even perhaps leading to an increase in the mass balance of Antarctica. So no shrinking at that time, that would be perhaps even glaciers growing. So I landed in Boulder, Colorado, and that's actually why I have this gown. It's the buffalo color from the University of Colorado at Boulder. and got immediately involved as a postgraduate student, a PhD student, in this Parker program, the Program for Arctic Regional Climate Assessment. And their game was to try and figure out the mass balance of the Greenland ice sheet. Is it growing or shrinking? And they were doing that in lots of different ways, observationally, but the big thing that they were doing was looking at it from aircraft and space, so remote sensing. And the big thing here was airborne laser altimetry. So an aircraft with a laser on it flying over the ice sheet, measuring the distance from that aircraft to the surface. And if you do that over repeat surveys, you can understand whether it's increasing in height or lowering in height, which gives you a sense of whether it's losing or gaining mass. And we were sort of parked up in this part of the equation as a research group led by Connie Stephan, the surface energy balance and understanding the climate. And so IPCC and the consensus in the 90s was that there was these big ice sheets were in balance. But this work by Bill Crable, he was based at the University of Kansas at the time. He was behind the laser altimetry from these P-3 aircrafts, the NASA aircraft. And this paper that came out in the late 90s, 1999, started to change the game. And they realized that the southern part of the Greenland ice sheet was really responding to a warming signal, and that it was lowering, and there was certainly a retreat. And from this observation, from aircraft, using those, it sort of spawned a whole new interest in what Greenland might be up to, and is it actually responding to climate change? So as a postgraduate student or PhD candidate, I was in a research group led by Connie Stephan, who was from Switzerland, a Swiss professor, ended up in Boulder, and very much a field-based climatologist. And I worked closely at the time with Jason Box. We were both PhD students. And I arrived in Boulder in January 1999, and I was basically deployed to Greenland in March 1999 after a couple months, and spent 3.5 months on the Greenland ice sheet, primarily on that trip servicing weather stations. So Connie had set up the GCNet, the Greenland Climate Network, which was a series of weather stations across the ice sheet. And they needed to be serviced. The ice sheets up in the accumulation zone tended to get buried, so you had to raise them, otherwise you'd lose them. And the ones around the margins of the ice sheet were melting out, so you had to lower them and re-drill and make sure that they didn't fall over because of all the melting ice. It was a lot of field work, and really remote field work. We did all of our logistics, which is different to Antarctica. We got to Greenland, we chartered the flights ourselves, we made the weather calls, and we ended up staying in these little remote camps. And I do remember being up at this little camp here, Humboldt, back in May 1999, and getting a little text message that Emma's first son, Benjamin, was born. And I remember walking out of that tent and looking out across the ice sheet and thinking, wow, that's an amazing thing. We were really remote. There's a couple places I just want to point out. Summit Greenland, which is at the top of the Greenland ice sheet, the Petermann Glacier, which is in northwest Greenland, and also Swiss Camp, which I'm going to talk a little bit about. Swiss Camp is a more established camp, and then we had a whole series of weather stations down in the ablation zone from there. So up to Summit now, just to the top of the Greenland ice sheet quickly. In the late 1980s and early 1990s, they drilled 2 ice cores to bedrock. That involved drilling through 3,000 meters of ice and allowed them to reconstruct climate through to the Eemian, which is the last interglacial about 125,000 years ago. A massive achievement, and started to kind of change people's understanding of how the ice sheet had behaved over that kind of time scale. But in the meantime, they realized that they couldn't quite understand all the chemistry. You know, what chemicals ended up in that ice core, how did they go from the snow or atmosphere and reside back into the ice? And so there was a flurry of activity with snow chemists working up at the top of the Greenland ice sheet, trying to better understand how some of those chemical species actually ended up in the ice core. So they called on us to take some turbulence measurements, which are basically understanding how we have exchanges of heat, moisture, and some of these other chemical species to really get an understanding of the wind pumping and the exchanges of some of these things. It was tricky work, and the snow chemists really wanted these eddy diffusivities or exchange coefficients. They wanted me to tell them what that wind or turbulence was doing so they could figure out how that snow chemistry was behaving. But I was getting worried because it was a really difficult environment to take those types of measurements. You have a very stable atmosphere, but also unstable, which is quite unusual over snow. The other challenging part of it was that the turbulence was really intermittent. So it would be really stable and nothing would happen for a long time, and then you'd get these little flurries of activity, which I'm trying to demonstrate with this plot, which just shows you a 30-minute time sequence, which has, in this case, 90,000 values, because we were measuring at 50 hertz, 50 samples per second, to try and capture this turbulence. And you can sort of see nothing would occur, and then suddenly you get this activity. This ended up being the focus of my PhD, and there was a moment there when I was working with the snow chemists, desperately trying to generate these flux values for them. And I had a visitor from Switzerland, Matthias Rotok, who's now leading the climate group there. And we went out for a lunch, and I was sort of telling him, hey, I'm really finding it quite challenging to make sure that this theory, which we're working with up there, is actually working. And he said to me, well, maybe you should stop trying to do that and actually flip that problem on its head and show people why it's so difficult and what some of those uncertainties are, rather than trying to just show that it does work. And it was just one of those simple moments, and it stuck with me because I think we end up doing a lot of that with us, as with our students, reframing problems, thinking about how to turn them around, and sometimes they're right in front of you, but you don't really see them. Matthias Rotok really helped me with that one. But the real action actually was going on around the margins of the Greenland ice sheet. This is where the melt had been detected and we knew things were going on. And so this is just a little project that occurred up on the Petermann Glacier, which is a large outlet glacier in northwestern Greenland, 70 kilometres long and 20 kilometres wide, discharging about 12 cubic kilometres of ice per year. 70 kilometres long is about the drive from here down to Balclutha. That's the length of this part of the ice tongue. 20 kilometres wide is about the full length of the Otago Harbour. It's a massive, massive floating body of ice that is discharged from the Greenland ice sheet. We went there and did some field work, and we really wanted to understand how much melting was occurring at the bottom of that floating tongue. No one had ever been there before. We weren't too sure whether we could land in there even with these twin otters. And Connie, my supervisor at the time, was trying to get some support to do it, but the rumour was amongst the graduate students that it was going to be a really horrible windy sight. And so no one really put their hands up. But it ended up not being that at all. It was beautiful. So this is where our site or camp was, and we first set up 2 little tents. We had polar bears potentially visiting the camp, so we had to do some practice with rifles. And this is a picture of Eric Rigneau, who's quite a famous glaciologist. And it was funny watching him getting instructions from Connie Stephan how to fire a rifle. It was probably the first time I'd done it too. Luckily, we never saw any polar bears. This is what these kind of camps look like out on the ice sheet. And inside, this is sort of how we lived. Not too different from a camping setup and if you're on a summer holiday, there's the gas cooker and other bits and pieces. Here was my little computer with the data loggers and everything else that I was using, and the very important bread maker, which was next to my office space. It was wide and open out there, and we had to do a lot of work just moving around out on that massive floating ice tongue. We worked long hours and sometimes through the night, and it was exhausting. And there were little surprises everywhere we went on Petermann. It's a remarkable and beautiful place. And I'll never really forget that field work. But there were dangers too. There were difficulties when we were moving around out on the Petermann. There were lots of things that you had to be careful of. We did ground penetrating radar, which allowed us to see through the ice to work out the thickness of that floating ice tongue. So we have a body of ice that's been discharged from the ice sheet, and it's floating on the ocean. And we used that ground penetrating radar to see through. And what we discovered was it's not flat underneath there. There are large valleys and grooves, and there was a lot of melt occurring. In fact, about 20 meters of melt per year underneath the ice sheet, or the floating ice. And that was the beginning, I think, for Greenland of understanding that the ocean can really interact with our ice. And there was a lot of activity, of course, then down in Antarctica doing similar things. But we were seeing that in northwestern Greenland. And we were also doing some observations, meteorological observations. Again, I was busy trying to understand how much melt we had on the surface as well. And we calculated that as being about 1 meter per year. So it was losing mass, but most of it was occurring underneath. The ocean, the warm ocean, was melting 20 meters per year. The atmosphere and the surface only 1 meter. So that was starting to transform our thinking a little bit about what some of these physical processes really were that were controlling this acceleration and retreat of ice. After I left, Petermann changed and a large fragment broke off in 2012, indicating instability and questions being raised about the long-term stability of Petermann. And just to leave Greenland, Swiss Camp was that little camp on the western margin of the Greenland ice sheet that I talked about. And it was a site that we would do a lot of intensive field observations. And when we used to arrive, we would arrive and see it like this in the early part of the summer. And often involved trying to dig out these tents here and doing a lot of work just to kind of get that camp going. But through time, they were confronted more with this. And so if anything is an indicator of how much melt started to occur in Greenland, this little simple demonstration really shows us that things were changing in Greenland, and that station that used to get buried is suddenly melting out on the western margin. And it was in 2020, in August 2020, where my supervisor Connie went back to try and disestablish that camp. It was falling apart, and the weather was poor. It was in that period of COVID. They should have been up there earlier, but they went in late. And in that field trip, he fell into a crevasse, and we lost Connie. And his legacy, Swiss Camp legacy, ended there. And it was a tragic event, but said something about really Greenland and what had happened in Greenland. And a year after, his son Simon and his friend went back and completed disestablishing that camp, and now it no longer exists. But I spent a lot of time there with Connie, and he was quite a remarkable person. After Boulder, Colorado, I moved to Innsbruck, as Rachel said, and started working with a group interested in Kilimanjaro, which is the highest freestanding mountain in the world, and has glaciers on it. The snows of Kilimanjaro, as Hemingway has written about. And it's a large volcano. It's about 5,895 meters high, and it has an interesting group of glaciers which are quite complex. And Kilimanjaro became a bit of an icon for global warming, and especially after a published paper by Lonnie Thompson. He was a big ice core guy, and he extracted a lot of ice cores out of the tropical regions. And he published this in 2000 and talked about the evolution of that ice cap over the Holocene, like the last 10,000 years, but predicted that those glaciers would disappear by the 2015 and 20, which was really established by just putting a linear regression through some of the retreat rates that they'd mapped. It irked the person that I ended up working with, Georg Kaza, and postdoc Thomas Mölg, who's the person now I've done a lot of work with in Erlangen. And so they wrote this concept paper to sort of set the stage, to sort of say, hey, we need to go back to Kilimanjaro. We should think a little bit about what some of those processes really are that are controlling that retreat. So a typical glacier looks a little bit like this. You'd expect snowfall at the top, perhaps across the whole glacier. Most of the melt occurs at the bottom. We have a series of energy exchanges that control the melt and other things. But the thing about Kilimanjaro, it looks a little bit more like this. You have these unusual fragments or little pieces of ice. And what makes them quite different to your regular glacier is that they have quite steep cliffs or vertical walls. And once you have those in a place like Kilimanjaro in the tropics, it's hard to prevent or stop the retreat. So I'll take you for a quick scenic trip around Kilimanjaro. We did this flight in 2005, and so you can kind of see what was left at that time. Here's the southern ice fields. You can see they sort of look somewhat like a traditional glacier in this regard. And there was still ice there at that time, but you can see that it was fragmented. Here is the eastern ice field. There's only little parts of it left. You can see the discoloration on the ground where the ice used to be, but has retreated and disappeared. And there's the northern ice field, the largest ice body still on Kilimanjaro. But you can see how there's these little features here. These are these quite unusual cliff-like features. They're quite tabular. And so we set up this kind of framework, which has been something that I've continued with students here, is we want to understand the atmospheric controls on those glaciers, and we want to link those to large-scale climate. And there are different pathways to link large-scale climate to the smaller scales. You can do it statistically or dynamically, and it's probably where I've spent a lot of my time trying to disentangle the large-scale climate signal to what's happening on the ground. And of course, Kilimanjaro has this complexity because we've got these funny little remaining ice bodies, little blocks. So this is how it looks on the ground, and we did field work on Kilimanjaro. Here is Georg walking up against one of these cliffs. Quite unusual. Lots of little jagged features which demonstrate that this environment is not dominated by melt, but sublimation of ice, which is the phase from solid straight to vapor. If it was melting along these surfaces, you would see much more rounded edges and much more rounded slopes. And we installed a vertical wall station here next to one of these cliffs in January of 2005. And it was your classic weather station setup. We had these radiation measurements, and they were important because one of those was a pyrgeometer, which allowed us to measure the temperature of that ice surface. And we also had an instrument here, which was a sonic ranging sensor, which allowed us to measure the distance from that sensor to the vertical wall. Unlike Greenland, where I worked remotely and often on my own in these remote locations, this was fabulous. I had a team of guides and lovely Tanzanians who would help me. And it was tough up there at almost 6,000 meters. It was a difficult environment to work, and I'll always remember the friendships that I made working with those guys. So here's just an example of what happens along one of those little cliffs. So this is 1 year of data from March 1 year through to March the next. And on this y-axis we have distance from the weather station to the cliff, and the other solar declination. And so the shading here represents the period where that cliff is mostly in shade, and you can see the distance doesn't change very much. But once you get into a sunlit period, that retreat really rapidly increases and you get melting along that wall. And so we were able to measure directly just how much are those ice walls retreating per year. And it turns out it was about 70 to 80 centimetres per year, or about a metre. So once that thing starts, there's no way you can really prevent it. And you will see a retreat on those at that kind of magnitude through time. We also use photogrammetry, which is a series of photographs at the cliff, taken at one point in time and then returning to see them again, which demonstrated that there's variability along those cliff faces, but there's a coherent signal between sunlit versus shaded. Once you end up with cliffs like that in an environment like that, there's nothing you can do. There's only retreat. And I think that's one of the unique parts of the retreat of ice on Kilimanjaro. We also worked on the southern ice fields, and I ended up having to install one of those weather stations in that period in January 2005. I was up there with Thomas Merg and Gail Kaza. Both were unwell on that day, so I wandered over to the southern ice field on my own. And I still to this day remember peering down that slope of the southern ice field thinking, am I going to go down there and try and install this weather station? But it was a beautiful view over the African savanna. I eyed it up again, and I did end up wandering about halfway down that southern ice field and found a location which I thought would work. It wasn't too steep, but it was reasonably testing, and by the time I got back up and talked to the guides and said, I've got a spot, I think we should go down to this location, they just looked at me and shook their heads and said, we're not going down there. And so we ended up installing it at the top. It was hard work trying to get the brain to work and putting this logger together and wiring a data logger up at altitude. But Joel, who was a fabulous guy and I'm still in contact with, helped me install that weather station. And it ran for almost 15 to 20 years. And it was a similar setup, simple observations. The key for us being, again, these radiation measurements, which allows us to understand how much sunlight shines on these glaciers. We can then derive cloud cover and understand how cloudy it is. And we know what the surface temperature is, when it's melting, when it's not. And we use energy and mass balance models then to calculate how much mass is being lost. As Rachel noted, I went back 6 times in that period, and every time it was different. And you would go there and service those weather stations hoping that they were running. We didn't have telemetry, so it was always a bit of a open up the logger, connect and hope. And but we had a pretty good record out of there. And Kilimanjaro was different every time. And as you can see from these penitentes, these ice needles, it was often really sublimation dominated, not so much melting. And so we looked at the rate of retreat for the southern ice fields too, using one of these energy and mass balance models, and we were dealing with about 0.5 metre a year of retreat, much more down at the bottom of the glacier, but on average about half a metre. What we also did was some backward modelling. We asked the question, what was happening back at the end of the 19th century when these things were retreating initially, and found that the climate didn't have to be too different to today. Just small little perturbations can really make these things behave in different ways. If anything, we really felt the climate had to be wetter in the past than today. We're just not getting as much snowfall as we need. But ultimately, I think Kilimanjaro's glaciers are really just remnants of a past climate. And the retreat is irreversible, and I think we'll see them disappear. And I did some work here with Pascal Sergway. We revisited the mapping, had another look at those estimates by Lonnie Thompson, and I think it's more likely that most of these glaciers will be gone by the middle of the century as opposed to have already disappeared. And we put this animation together. This was really work done by Pascal. This is what it looked like in 1912. We had about 12 square kilometres of ice on Kilimanjaro, certainly covering all of the southern ice field at that time. And then the retreat began, and it hasn't stopped. Here's 1960s into the 1970s. You can see the Western Breach has these isolated ice bodies, but it's all starting to break apart, becoming isolated, and then really vulnerable to additional melting just because they're surrounded by ash, rock, and other things. And that brings me to my last little chapter and my journey here, I guess, while I've been at Otago, the accelerating retreat of mountain glaciers, and also just understanding that there's these widespread changes to the cryosphere. So when I returned, it was sort of the question I had to ask myself, oh, what's next? What shall I do? And we're all here, and it was exciting to have those Southern Alps in my backyard again, and so that became a bit of my focus. And my current areas of research are linked to mountain glaciers. So I'm into the glaciers thing still, but also seasonal snow and how they modify water availability in our largest drainage basins. And then I've got an interest in the McMurdo dry valleys in Antarctica, and I've got a couple of students working on that, Tamara up there, and also Marta, who's currently in the McMurdo dry valleys. I've only got time to talk a little bit about the impact on glaciers and the work that we're doing in that space. So mountain glaciers occupy about 200,000, there's about 200,000 mountain glaciers in the world, occupying about 700,000 square kilometres in the present. And if we took them all today and melted them, it would be equal to about 40 centimetres of sea level rise, which is only 1% of the total amount of land ice. The ice sheets are where most of our ice resides, Greenland and Antarctica, but they're still important contributors to sea level rise today. And so we have quite a strong interest in them. Their contribution as a proportion to the total amount of sea level rise is actually still quite high, comparable or equal to the ice sheets. So that area is about the same size as New South Wales. And as I said, they are important contributors to global sea level, accounting for about 17% of the sea level rise that we currently observe. So then I had to sort of think, well, shall I tackle this problem at a global scale? Would that make sense? But there's quite a big community out there looking at the retreat of glaciers at a global scale. So it made more sense to me, I think, to focus on the local and regional impacts of glacier loss, how they'll impact stream flow, modify stream flow properties, and other processes. But I do, before getting into that, I just really want to briefly tell you a little bit about what that global glacier modelling community does, because it's an interesting exercise. How do you go about trying to understand how our glaciers at a global scale are retreating? First, you need to know something about the global climate, and you use reanalysis or these global climate models. But they are run at a really large scale, so you have to downscale, you have to come up with some sort of method to make that data more representative at a smaller grid scale. And there's a lot of work involved going from global climate down to local climate. Then you have to run a little glacier model, and you need to know something about the surface mass balance. What is controlling that glacier? Is it going to grow or shrink? And what are the controls on it? Temperature and some of these other energy exchanges. You also have to take into account the geometry changes of that glacier once you start to understand whether it's growing or shrinking. And there are some tricks doing that too. It's not that easy to understand how those changes are occurring over time. Once you do that, you can calculate the volume change, you sum all of that up, and that gives you an estimate then of the contribution of ice to sea level rise. And it's that framework that allows people then to make these projections that we see at a global scale. And this work comes from Ben Marzion, who I work with in Innsbruck. The projections then, what are our glaciers on a global scale going to do in the future? How much ice loss will we see by the end of this century? And you can see that it's dependent on the emissions scenario. What is our pathway? And the IPCC and some of these other agencies have different emission scenarios. A low emission scenario where we would be curbing our emissions, which we sometimes refer to as RCP 2.6. 2.6 actually being the radiative forcing in watts per metre squared. Or we don't do very much at all, and we allow those emissions to run away on us, and that radiative forcing will be much larger, RCP 8.5. And so depending on that emission pathway, that'll dictate to some extent what those glaciers will do by the end of the century. But on a global scale, we're looking at about an 18 to 36% change in the amount of ice that we will have, which equals about 8 to 16 centimetres. What's interesting though, is if you look at the small glaciers, the pockets of small glaciers in places like New Zealand and Scandinavia, because there's much less mass and they're at mid or lower latitudes, the projections suggest that much more ice in those regions will disappear. And so for a place like New Zealand, we would expect by the end of the century about 80% of our glaciers to have disappeared. And so then you can start considering the uncertainty in those estimates. And Ben came up with this plot which shows us what is the uncertainty going into all of this modelling from 2020 through to 2100. And he broke it up into 4 components: the glacier model uncertainty, the climate model uncertainty, the emission scenario, and the natural variability. So have you got the right model at a global scale for your glaciers? How's your climate model going? Do you understand your climate? Do you have a handle on the emission scenario? Do you know what the emissions will be? And the natural variability, what will that be as well? And so in the present, it makes a huge difference what glacier model you end up using, because in the present, we actually have a reasonable understanding of our climate. So much of that uncertainty is associated with the glacier model. But as time goes on, it's the emission scenario that will dictate the variability, much more so than the glacier model and the input uncertainty. I'm giving you a little bit of that detail because it sets the stage for where I've tried to centre my research while I've been at Otago. So what are those key uncertainties and how should we be handling them? You've got global climate, you've all these biases in those global climate models. We don't quite understand how some of those things work, so we need to evaluate them. That downscaling, trying to connect the large-scale climate down to the local climate, is a challenge. You can use different methods to do that. The geometry, we use quite simplified models to try and understand how those glaciers will change in size and dimension. And we could use then more physics-based models to try and to account for some of that complexity. But it was the surface energy balance, that model uncertainty, that I thought maybe we can make a contribution in that space to improve those models, to make sure that those projections are more robust, moving from quite simple empirical models to more physics-based models that really allow us to disentangle some of the surface energy exchanges. So my thinking was to place myself in this space when I got to Otago, to try and tackle some of those problems, not up at the global scale, but trying to understand some of those processes at the surface mass balance and local scale. And so to do that, we set up a program in the Southern Alps at Brewster Glacier, which is just west of the main divide. It sits under Mount Brewster, which is at about 2,400 metres. The elevation down here is 1,600 metres or so. And at the end of every winter, we go up there and measure first the snow density by digging snow pits. And we also do a series of probes that allow us to work out how much snow actually fell on the glacier. We then install ablation stakes using steam drills, which are basically drilled into the ice, 10 metres into the ice, that allow us as measuring sticks to work out how much of that snow and ice actually melts over the summer. And that gives us the mass balance. It tells us what the inputs are and what the outputs are. And it's just provided us with a baseline for the modelling and other observations that we do. The field work is relatively simple, but can be logistically demanding. It can be quite complicated there up at times. My view is that probably one of the more important parts of this field work is the opportunity it has given me to get graduate students and other students working in these kind of environments. And the students, I think, that have had the opportunity to be up there have experienced Brewster and been able to see some of those things, those physical processes firsthand. And it really, if it wasn't for this team of people, I don't think we would have got all of that work done. We've put weather stations up, much like the ones that I have put up elsewhere, on the glacier and next to the glacier, allowing us then to work out how much melt is occurring. Back to turbulence measurements, which I did for my PhD, and help us resolve some of these complexities in the modelling space. Really working then on the energy balance, the atmospheric controls on melt, and the large-scale atmospheric forcing and the connections to the glacier, a similar framework that we were using on Kilimanjaro. And from that, I think we really have established a bit of a benchmark for Brewster. I haven't got time to kind of go through all of the work that we have done, but we really, I think, have produced a volume of work that has allowed us to advance our understanding about how Brewster's behaving and how glaciers in the southern hemisphere are behaving. I think the key contributions really have been to characterize some of those energy and mass exchanges directly. So going from those simple parameterizations to explicitly resolving them. And that's really helped reduce modeling uncertainty for us, and then allowed us to make those contributions to the global community about how to model some of those things. They've also, those observations have provided a lot of information for the validation and calibration for the remote sensing observations. It's allowed us to dig into some of those techniques about how you downscale from large-scale atmospheric circulation to the local scale using different methods. And it's spawned a whole other area of interest around how some of these extreme weather events, which have started to impact us all, how those events are contributing to big snowfall events, big snow melt events, and a number of my students have targeted atmospheric rivers specifically to try and characterize what is controlling the variability of these glaciers. Just to finish on a little note about one of the more simple observations, we used an energy and mass balance model to reconstruct what Brewster has been doing over the last 40 years. So from 1985 through to the present, and on the y-axis here we've got annual mass balance, and we've got cumulative mass balance here. And so if you're in the blue, the glacier is growing in that year, and if you're in the red, the glacier is shrinking over that time. And you can see that since about the around 2006, 7, 8, things changed, and we've seen a significant decline in Brewster Glacier and the glaciers more broadly across the Southern Alps. So we're losing 3 times as much mass since that time than we were previously. So we've gone from about 0.5 meter or 0.4 meters of lowering of ice to about 1.2 in that time. And if we look at it as a cumulative loss, that's about 30 meters since the 1980s. If you think of the diving board down at Moana and you go to the top, that's 3 of those in height and loss. So they are rapidly retreating. And just to put a visual marker on that, here's Brewster in 1983. This animation, or these images, have come from the EOS program, which Gregor Makara, who is here, and Andrew Laurie have been responsible for overseeing, and more recently. That's Brewster in the mid-80s. There's 1997, 2006, 2016, 2022, and then in March this year. You can really see how much ice has disappeared, and these areas in the upper part of the glacier, which you'd expect might be holding on or hanging on, are definitely just breaking up. There is no accumulation zone, I think, anymore in the Southern Alps. And so when I go back to this global scale plot, which is being produced by colleagues like Ben Marzion using globally gridded data, and I look at those different emission scenarios and their projections for glaciers in New Zealand, and this is indicating that if we get our act together, we can prevent that glacier loss, perhaps restrict it to about 40%, but if it was business as usual, it would be 80%. My gut feeling at this point, based on what our observations are at Brewster, is I don't think the emission scenario will make a difference. I think the pathway is retreat from here. I think they're so out of equilibrium that they will continue to disappear. We may still have pockets at the highest elevations in places like Mount Cook, but a lot of our other glaciers will be gone by the end of the century. What are we still struggling to have a handle on? Precipitation. We still don't really understand how to measure it properly, and if you're in the modelling game for glaciers, it's a real pain. But luckily we've got former postgraduate students from Otago, Peter Gibson and John O'Conway, working on those problems, have been recently funded and have come up with some pretty clever ways to address some of those things. Machine learning, artificial intelligence, to try and improve how we understand our mountain climate. So I'm really encouraged that next generation of climate scientists are going to solve some of those problems for us. So I will end there and say that over the last 50 years, or my lifetime, I think we have developed a much greater understanding of the impacts of global warming on our cryosphere. We now really know that the ice sheets are contributing to sea level rise. They are changing. Greenland and Antarctica have awoken. The retreat of mountain glaciers has accelerated, and many of our mid-latitude and tropical glaciers are expected to vanish this century. I haven't had time to talk about sea ice today, but we're seeing drastic changes in sea ice in some of the other parts of the cryosphere, so change is afoot. But I think the benchmark measurements that we've made on Brewster have been useful and have provided a really good framework to do some of this work in New Zealand. And I am hopeful that it's also provided a platform for that next generation of climate scientists that I'm confident will solve some of these problems for us, or at least allow us to understand how we might go about reviewing, disentangling, and to sort of establish a better understanding of what our future holds. And my last little slide is this: it's not all doom and gloom. I still think these places have great value and can still be enjoyed, and I will endeavour to continue doing that with my family, and I think we all should. They will be changing, but there's still lots of fun to be had up there. And I'll end with that.
Tēnā koutou katoa, ko Jessica Palmer tuku ingoa, ko te manakura o te Kita Aranui, o te wharewananga o Otago whakaihiwaka tēnei. So it's my great pleasure as the Pro-Vice Chancellor of Humanities, which is the division that Nicolas and the School of Geography happen to sit in. We can have a discussion later about why that is. There are many in this room who have views on that. But nevertheless, for tonight, it means I have the pleasure of congratulating you, Nicolas, and to give you a vote of thanks and confidence on behalf of the university. I think that was a stellar lecture, don't you? And I think what it beautifully presented is how important research is, and that it really matters, and that Nicolas's career is a story of how researchers don't just solve problems, but they identify problems and questions that need further solving. And lovely that you ended with exactly that. Here are the things that we've discovered need to be researched even further. And you showed us that research is complex, that it's detailed, and that it takes years of commitment. So bravo to you for that. There were two things in particular that as I watched you in flight, I was reflecting on. And one is that, no, three things actually. That research, and some of the best research, is a dialogue. It's a dialogue between our personal stories and our own interests and questions and knowledge and ideas. And again, Nicolas started and ended with that. The things that make him who he is, and his family and his own personal experiences, are what have motivated his research. And so I want to say thank you for being true to who you are and for exploring that in your research. Secondly, great research depends on being communicated really well. It's one thing to sit in your lab or in your office, or if you're lucky to be like Nicolas on an amazing glacier somewhere, but if you can't explain that and tell the rest of us why it's important, it's a bit of a shortcoming. And tonight Nicolas demonstrated, I think with real class, that he communicates his research exceptionally well. I go to quite a few IPLs. This one had 96 slides in it. That is definitely a record of all the IPLs I've seen, and yet I don't think any of us thought, when is this finishing? It was just beautifully crafted, and so much information in there. You dovetail beautifully between personal stories, lovely to see Susie appearing in there, and also some very technical information, and you took us with you, so bravo for that. And then thirdly, for me, I think the other important thing that you emphasise for us is that research and knowledge are not static, and that they are the subject of theory and change and a dialogue, and that you've shown us that theories on glaciology, meteorology, climatology are needing constant research. And so in a sense you gave a great plug for the role of universities and the role of research institutes. We can't stop, we have to keep going. And I wish that there were several politicians in the room tonight to be reminded of just how important funding research in this country really is. So Nicolas, I want to pass on to you some well wishes from Etienne, who is the head of geography here and unfortunately couldn't be with us tonight, and he passes on congratulations. And I want to say to you on behalf of all of us, whakamihi kia koe, congratulations, ahorangi Nicolas Cullen. I have somewhere here a wee koha from us, which is a little sign of appreciation to you, but also a marker of what is an historic night.
Thank you.
Congratulations.
Thank you so much.